We are living in very dangerous times. Imagine a company with 1,000 employees. Imagine that every single employee of that company having like a personal assistant. This attack is becoming very, very common in the US. And it's extremely hard to detect.
If humans actually stop paying attention once the AI is running, then how does the common advice which says just have humans check the AI's work, how does it work?
Doesn't work. At 10 to 20% attention span, you're not going to be able to respond. But the ones that were using the LLM, they could not reboot their brain. I basically recommend organizations turn off cloud coding at least once a week.
So aren't we just replacing one unreliable watcher with another? That was Claudio. Welcome to the Spark and the Forge podcast. I'm Subrata Kar. You know, this is someone who spent 30 years doing this. Stanford PhD in formal verification, basically making sure the semiconductor chips behave correctly under every possible conditions. And think about that for a moment. Every possible conditions. At Google, he built Q-Keras for model quantization. His work has been used in systems supporting experiments at CERN, the Large Hadron Collider. And these are physics experiments that just can't tolerate errors. VP and Fellow for AI at Palo Alto Networks, Chief AI Officer at Advantest, and that's where he coined the term True Zero Trust in 2023. Then Chief AI Officer at Zscaler through December 2025, 500 billion transactions daily. And he saw what breaks at scale. And now he is a Senior AI Fellow at Majestic Labs, building next generation infrastructure for high-speed inference and agent execution, advising Ridge Security on agentic penetration testing and Daxa on reasoning layers for secure AI agents. Now, so here's the thing. Everyone is deploying AI agents right now. But you know what? 95% of the pilots never make it to the production. And it is not because the AI fails. It is because the security breaks, the reliability breaks, the governance breaks, something else breaks first. And now the insurance industry is telling us that they won't even cover it. So I wanted to understand what's actually going wrong and what the small percentage who aren't failing are doing differently. So I sat down with Claudio to find out.
What I have been telling people for more than 3 years now is that building agentic systems is a software engineering problem. It's not an LLM problem. Remember, in reliability of computer systems, when you took the man to the moon, we used to say that if you connect all those computer systems in series, if one of the systems fail, the whole thing fails. Now, let's transport that to 2016. Imagine that you have a multi-hop agentic flow, and the agentic flow basically have to search for information on several hops, several states. If one of those states fail, it's the same problem when we took the man to the moon more than 30 years ago. And people are failing to discuss those problems. It seems that people have forgotten that those are engineering problems that have been solved in the past.
You see, that's an interesting way to think about it. This isn't really an AI problem, as Claudio puts it. It's an engineering problem. And here's the thing. If it is an engineering problem, the solutions already exist. We have seen this before. Moon landing, aviation, semiconductor systems, environments where failure is not an option. The difference is these systems were designed with failure in mind from day one. Redundancy, validation, clear guarantees on how the systems behave. In AI, we move too fast on scale before we really engineered how these systems fail. And that's where things start to break, because the architecture most companies rely on is zero trust. And that was built for a completely different world, system that behave predictably, where you more or less know what's going to happen next. But now you are dealing with thousands of agents talking to each other, making decisions, passing context in ways that you can't fully trace. So what happens when you take those old assumptions and apply them to a system like this?
So I'll give you an example. If you have like a mid-sized corporation, spend a lot of time qualifying suppliers of APIs. Probably this corporation has Gmail or Outlook. They have like Salesforce. They have ServiceNow or Slack. So they have like 50, 100 APIs that they have connected. Okay? And even if someone attacks the Gmail, this person will have to sift through a large number of emails until he or she finds the information he's looking for. Now, I was doing a presentation at MIT last year to the Nanda project, and they're claiming that by 2034, something like that, we are going to have trillions of agents running everywhere. Each one of those trillions of agents, they're going to be connecting through MCP, through A2A, and it's going to be a mesh. It's a new internet. Imagine now that now you have not to have to qualify 100 APIs, but you have to qualify 20,000 APIs. First of all, no company is prepared for that. In zero trust, there's a basic principle that the most secure data does not leave the trust perimeter of the company. Now, with those APIs running on MCP or running on anything, you're trusting that your most secure data is going to be, you're opening I call this floodgates to hell. Okay. You open the gate and you start sending confidential information to that MCP connection. And that MCP connection is people on the other side.
Floodgates to hell. Think about that. You see, zero trust protects the pipe. It makes sure the connection is authenticated. But here's the thing, it has no option on what it happens to your data after it arrives on the other side. None. And the MCP, the Model Context Protocol, connections multiplying everywhere, you are not sending the data to 50 vetted vendors anymore. You are sending it to mesh where other side is completely opaque. So what does an actual attack look like in this world? Claudio walked me through something I honestly hadn't considered. How small vulnerabilities, the ones that nobody would flag on their own, combine into something no human security team would never think to test for.
But one thing that I do is that I do not open any type of information from me on OpenClaw to run. Because we don't know how people are going to attack. We're basically in a brave new world, and people are still figuring out how they can attack. So last year, there was an attack that was staged using Anthropic tools, and this attack was based. Imagine this. The reason why I mentioned Swiss cheese is that it used to take a person, very skilled person, to stage an attack and try different CVEs, try different types of attacks. Now, if I basically put this coding agent with me without any skill, the only thing I need is basically like my mother language, my spoken language, and I can start checking with it, saying, instead of using a high-risk CV that people can probably block very quickly, if you basically stage an attack using those very low-risk CVs together, and by staging them together, it becomes a high-risk thing. That's the Swiss cheese that I mentioned. And because of that, you need a new type of security machine. So think about that. Before, people used to do what I call like a single type of attack. So if it's a DDoS attack, they would do a DDoS attack and that's it. Now, imagine that like you have like a whole agentic malware that will try to do different types of attacks, like smaller DDoS together with SQL injection, and figuring out what is the timing you need to put on those things to break the timeout on the server, so that something else would try to do it. And by doing that, they can basically enter the system. So it's something that other humans cannot think about all possible combinations. But someone using an agentic flow to try to create an attack, remember, attacks are free. If they create one, it fails, they can create another one, and then they keep creating another one until one passes. So we need a new type of agentic security company.
That's a shift right there. Attacks are no longer one thing at a time. They are composed, layered, and they are cheap. And agentic attackers can run thousands of combinations in the time it takes for human pen testers to run only one. But here is what caught me off guard. I assumed that the problem was just on the attack side. We need better defenses. So the Claudio pushed back on something more fundamental. The AI system themselves, the LLMs powering these agents, they have hard boundaries that they can't cross. And most teams don't even know it is there. And here is the reason for that. In computer science, there's a class problem called NP-complete problems. And these are problems where the number of possible solutions grows exponentially as the system gets bigger. Think about something very simple, like a delivery truck making multiple stops. With 3 stops, you can try possible routes. But with 20 stops, the number of possible routes becomes so large, even the best systems can't realistically evaluate all of them. So what do? They approximate. And that approximation works until your system needs to be exactly right.
Usually the way that I say is this. We humans, we know when something is probabilistic and something is not probabilistic. I basically use this example. If you turn on your self-driving, like a Tesla or any other self-driving car, and if the self-driving sees a stop sign, it cannot stop on the stop sign with 99% probability. It has to stop at 100% probability, because if there is a child crossing the street on this 1% that is going to fail, it will have a problem. We will have a problem. Okay? So there are certain things that probabilistic reasoning works very well, especially when you're dealing with fuzzy information. But there is another type of problems that we call like discrete systems, and LLMs cannot solve those systems reliably. And the example that I like to do is this. Sometimes people pose some questions, and the question that I like to use is this. Suppose P implies Q. Q is different than it's false during the day, and it's day now. And then the LLMs will say, okay, because you basically build a logic game on this, you're going to conclude that P must be false. Because it's day, since Q is not true when it's day and it's day now, then Q must be false. Now, imagine that we change one of the words. Instead of saying it's day now, you say it's sunny now. In India, sunny and day are probably very similar words. But if you are in Stockholm in the summer, the sun never sets. So day and sunny have completely different meanings, because it's night, and because humans are very good into basically understanding the nuances of the language and understanding that there's a context here, and I need to bring the fact that if you're in Stockholm, probably those 2 words don't mean the same thing. LLMs don't have that ability. And they do not traverse very well when you migrate between probabilistic into discrete. They stop. They are always probabilistic.
So think about it. Probabilistic systems cannot guarantee discrete outcomes. And that's the line. If your business has rules that absolutely must hold, like accounting equations, compliance thresholds, safety constraints, and LLM alone cannot enforce them. It can get close, but it can approximate. But close is not the same as correct. Not when a child is crossing the street, not when your book needs to balance every sense. So where did the idea of enforcing absolute rules in AI systems actually come from? Claudio took me back to where he coined the term true zero trust. And contrary to what you might expect, it wasn't in cybersecurity. It was on semiconductor manufacturing floor.
Yeah, so very good question. So when I created this term true zero trust when I was at Advantest, and we are basically building semiconductor manufacturing equipment. And because we know very well in a manufacturing environment what is the traffic that goes on, we can basically enforce this very, very tight rule. And we don't, for example, suppose that we decide in zero trust to protect your laptop. Now, if you go to a manufacturing setting, in manufacturing, what happens is that we know exactly what is the traffic that is going to happen in that machine. And because we know in the manufacturing what is the traffic that goes on, we can basically stop the machine if the traffic deviates anything. By 1 byte or 2 bytes, we can stop. That's why I call true zero trust, because we will not trust any byte circulating in the manufacturing floor outside what's your parameter. But I understand what you're saying is that with AI and Agentic AI, we need a new type of trust, because it goes beyond just saying, I'm going to protect the connection. I need to protect what people will do with your data.
Stop the machine if traffic deviates by 1 byte. And that's the standard he's working from. Now, you see, manufacturing is a controlled environment. You know exactly what traffic looks like, but enterprise AI is not that. But the principle carries over. If you can define what legitimate behavior looks like, you can enforce it. The question is, what happens when you move from the level of control to something that is much more open? And Claudio gave me an example that really made the gap real.
I'll just give you like a very simple example. Suppose that you have a public company. So they trade stocks. Okay? So usually the auditing company that comes to check your financials, some companies are so strict that they need a clean room. So the auditors cannot bring their laptops, cannot bring their cell phones into the auditing room. Okay. Now, some companies are offering auditing on agentic flows. So you are going from something that was extremely secure to something that you don't know where the data is going anymore. Oh, you know where the data is going. But suppose now that the company that receives the auditing, the data from your financial, there is a rogue employee there, and he decides to store the data and start trading stocks of the company before the financial release. So that's, we need to find a balance, because we are going to an environment that was extremely secure, that you have no control. And when I say that we need a new type of zero trust, is because it's more than just trusting the connection. You need to trust what people will do with the data, or that they will not leak parts of the data afterwards.
You see what just happened there? From a clean room, auditors can't even bring a phone, to an agentic flow where you don't know where your financial data ends up. And that's the migration happening right now inside the enterprises. And most of them haven't fully processed what they're giving up. And you know what the common response is? Put the human in the loop. Just validate the results. So I asked Claudio to explain this autonomy paradox.
So I'm going to mention both the study they did on Tesla, and if your attention span when you're driving is 100%, if we turn on self-driving on the Tesla, this study is from 2022. They realized that attention span goes between 10 to 20%. So at 10 to 20% attention spans, if a child crosses the street in front of the Tesla and you need to take the wheel, you're not going to be able to respond. Okay. The Department of Transportation in the US, they require you to put the hands on the wheel. At 10 to 20% attention span, you're not going to be able to, I'm telling you, you're not going to be able to respond. Okay. Recently, there was a study last year done by MIT, and they put EEGs on the brains of people, and they gave the people it separated the group of people into 3 groups. Group 1, they had to solve a problem by hand. Group 2, they could use Google to search. Group 3, they could outsource to the LLM. And then after they solved the problem, they had a follow-up problem. And the follow-up problem that was basically related to the problem they solved before. So people who solved the problem by hand, they were able to solve the other problem quickly. But the ones that were using the LLM, they could not reboot their brain. Their brain were, once they outsourced to the LLM, their brain went into almost like resting mode. So they did not know what to do. We are seeing that happening right now with vibe coding. Because with vibe coding, it's very interesting technology. Okay? You need to understand the limitations of vibe coding. I can give you like a 1-hour lecture on when to use and when not to use vibe coding. But one thing that people realize is that they lose control of the code once they start using too much vibe coding. So companies, if you want to use vibe coding, I think you should. But my response to people and to companies when they ask me this question, I say, turn off the vibe coding at least 1 day per week. So people need to read the code so that when the next outage in the code happens, they will know how to fix. Okay? Otherwise, the people will not know how to fix, which is exactly the same problem that you asked the question.
The brain goes into the resting mode. Think about that. You see, once you outsource your thinking to a large language model, your cognitive engagement drops so far that you can't literally recover when something goes wrong. And the vibe coding wave is accelerating this across engineering teams right now. And Claudio actually experienced this firsthand. And what happened next, honestly, every engineering leader needs to hear this.
I was doing like, I teach at Santa Clara University, and I was preparing a lab last year on reinforcement learning. And when I was preparing the lab, I wanted to fine tune the lab. So I wanted to add the new questions to the lab. So I asked one of those vibe coding agents to start helping me with the lab. And then after each step, they ask you, do you want to add this portion of code to your solution? 1, yes. Type 2, yes to all. 3, no. First time you say yes. Second time you say yes. And third time you say, I'm in a little bit of a hurry. I don't want to be able to have to yes everything. Everyone does that, by the way. Yes to all. So it continued to generate the lab. And the last message that I saw was this. The lab was created, everything working, deleting the lab. It deleted my lab at the end. So imagine that this was on the GitHub, or if this was like a database, it would have deleted the company database at the end of the interaction.
Deleting the lab, everything's working, then gone, because the system asked permission and the human said yes to all. We all have done that. Now think about it. That's university lab. Scale that to a production database, a customer-facing system, a financial ledger. The risk isn't just inside your system. Claudio shared something about the data actually ends up after it leaves your perimeter through API connections. And what he described, it really challenges this assumption we all carry. The secure connection somehow means secure data.
So I think OpenClaw, with that, what happens with OpenClaw recently is the most recent example that people put an agentic flow, autonomous flow inside your computer, and then secrets starts appearing somewhere else. Last year, there was a famous case on MCP security, and the idea was, it was like an Asana MCP connection, and the way that I position is this. Suppose you have a red customer and a blue customer. Both were connected to Asana MCP server. So the connection was secure because Asana is a trusted company. Inside Asana, there was a bug in the system that allowed contamination of data across multiple customers. So what happened was that data from the red customer appeared in the session of the blue customer. And then you can say, yes, but this bug has since been fixed. The answer is yes, it has been fixed. But you have to understand is that how many of those MCP connections people are sending data, this type of bug still exists. You cannot answer that because it's not about the connection. And what if a rogue employee basically decides that he or she is going to basically take that data out? In Brazil, I'm originally from Brazil. the largest one of the largest financial schemes that happened. There was a rogue employee in the company that was processing bank-to-bank payments, and that rogue employee gave the credentials to a hacker. And that hacker was able to infiltrate the whole bank-to-bank communication system. Now, transport that to a company providing MCP services to the 500 largest corporations in the US and being able to basically start stealing data. And it's not about trusting the connection. It's about having a secure space. We will need soon a secure space where data cannot live, a secure pod. And that does not exist right now. I said, well, best solution is MCP servers should stay inside your corporation, or at most in the virtual private cloud, but not outside your corporation, because you cannot guarantee security outside.
Red customers' data showing up in the blue customer session, a rogue employee handling credentials to a hacker on a bank-to-bank payment system, and his advice right now, keep the MCP server inside your corporation or your virtual private cloud. Don't send the data outside your walls. So think about it. If human oversight fails and your data perimeter is porous, then what's left? Claudio's answer is very specific. You don't guard the AI with humans. You encode the rules directly in the system. And some rules, they can never be violated, not even 1%.
Only by creating reliable systems that can give guarantees to the usage is that you can make sure that those systems work. Without this, without guardrails, and when I say guardrails, it's not guardrails on the data or on the connections. It's guardrails on the business. And the example that I like to use is accounting. In accounting, assets and liabilities is equal to minus liability is equal to shareholders' value. It cannot be equal to shareholders' value with 99% probability. It cannot be equal to shareholders' value with plus or minus 1 cent. It has to be equal to the shareholders' liability, period. We need, if someone is basically developing like an agentic flow that is going to solve some accounting problems, you need to have that rule encoded in the system somewhere. And that rule can never be violated.
Asset minus liabilities equals shareholder value, period. Not with 99% probability, not plus or minus a cent, period. You see, that's the kind of rule that has to be hardcoded into an AI systems, and you can't leave it to a probabilistic inference. You just can't. And this is where the math of multi-agent reliability gets really uncomfortable, because even if individual agent is highly reliable, 90% accurate, which sounds great, the system level maths tells a very different story. And Claudio illustrated this with a calculation and a personal story. And that honestly stopped me cold.
The example that I like to give is this. Suppose you have a multi-agent system. Each step of the multi-agent system has 90% accuracy. 90% accuracy is extremely reliable system. Okay? If each one of those hops, you have 10 hops of 90% very highly reliable systems. If you connect them together, the probability of the system failure is going to go down to 30%. The probability of the system working goes down to 30% because it's 0.9 to the power of 10, which is 0.35. So the system will fail very frequently. And the example that I like to give is this. I was booked on a flight from Air France from Rio to Paris in 2009. That airplane, the autopilot, when it was flying over the ocean, I canceled my reservation on the Friday, and the airplane crashed on the ocean on Sunday. Okay? Yeah. And that airplane, basically what happened was that it had 3 pitot tubes, one on each wing and one in the front of the airplane, and those pitot tubes was informing the speed to the computer systems. And it was a triple redundant system. Just like you could use an LLM as a judge. 3 systems acting as a judge. The 3 pitot tubes froze, and it put the plane head down to the Atlantic Ocean because it reported the speed being 0 on the 3 pitot tubes. First of all, it did not have world understanding, the autopilot, because if it had world understanding, it would notice that energy does not dissipate in zero time. So the computer system must have been going wrong somewhere. Number two, triple redundant systems work if errors are uncorrelated. And now, at the time, that error happened because the three pitot tubes were made by the same manufacturer. So the error was not uncorrelated. The error was correlated because the three of them froze at the same time. Now, if I tell you that I'm going to use LLM as a judge with different providers of LLM, and if those three LLMs were trained using the same data, can you confirm to me there is no correlated errors? So they cannot be used as LLMs of judge. We need to have another layer that will act as a judge.
So basically, companies fail since they just don't know how to govern and make really actionable insights. You made a phrase that I love, AI theatrics. So are you actually solving a business, or are you doing AI theatrics?
42% of the companies abandoned their AI projects last year, double from the year before. Not because AI failed, because production did. Impressive demos that break the moment they touch the real enterprise. I talk to people who actually deploying AI at scale, and I cut to the chase. What separates the ones that ship from the ones that store? No theatrics, just production. Intelligence without system is just compute. I'm Subrata Kar, and this is the Spark and the Forge. 0.9 to the power of 10 equals to 0.35. 10 highly reliable agents connected together, and your system works only 35% of the time. You know what? When you try to fix it with redundancy, LLM as a judge, triple checking with multiple models, the air fronts lesson kicks in. If the errors are correlated, redundancy is an illusion. Same training data, same blind spots, same failure. But here's the thing. There's another problem with the multi-agent system, and that's even harder to spot, the auditability problem. You see, when agents pass context to each other, the reasoning chain goes opaque, and a single popular data point can steer the entire output without anyone knowing why.
A few months ago, Jensen, the CEO of NVIDIA, he mentioned that quantum computing was 10 years away. I don't know if you remember him saying that.
Yep.
And that basically the next day, the stock price of all quantum computer companies went down by half. But assume that you have now an investment agent working for your pension. And that they may basically you ask the question, should I invest in quantum computing stocks?
Right.
And if one intermediate step of that research agent for investment basically searches for popularity of comments on quantum computing, because Jensen mentioned that fact, it's going to carry a lot of weight, because when you do an internet search, that is going to appear everywhere. What I'm saying is that that agent make an assumption based on the popularity of Jensen's comment will not be carried over to the next agent to create a portfolio for you. And because of that, you lose the ability to basically audit that decision. Multi-agent systems has a problem of it becomes harder to make like auditability of them, because they exchange information among themselves, and sometimes someone could steer the next agent to go in a direction that you don't know how it's going to happen. They're not going to say, I base this on the fact that Jensen is probably like a pod. Everything that he says reaches 10 million viewers, and I use the fact that 10 million viewers viewed his speech when he said that. And you're basically, you understand what I'm saying, right? To make a decision, you don't know why cause you to make that decision, because LLMs are very hard to cause like multi-step causality reasoning.
You don't know what caused you to make that decision. Think about it. That's the auditability gap in a multi-agent system. So look, We now have established what breaks. Zero trust doesn't cover the behavior. Humans stop paying attention. Reliability compounds. Audit trail disappears. And the question now is, what actually works? Claudio pointed me to two approaches he's advising on directly. The first one is reasoning layers that evaluate risk dynamically, not statistically.
So Daxa has a very interesting business proposition, and they just there's a video on the internet saying that they're putting right now a security layer on the OpenClaw or NemoClaw, so that the NemoClaw will not leak out information from you. And they do not look only at the connection, they look at what's being transmitted in the data when the agents are communicating to other agents. And they look at that and they make a decision. Oh, I cannot have this data sent out because there is a risk. It evaluates the risk. Remember what I told you before. It's a risk evaluation. So they evaluate the risk that this data can leak out, and then they block that data. But they dynamically may accept other types of data to go on those connections.
How the dynamic rule creation works, or some people call it neuro-symbolic approach. Can you explain?
When you're saying like neuro-symbolic comprises of solutions that uses symbolic AI or rules. Okay, it could be in the forms of rules, it could be in the form of knowledge graphs, and it could be in the form of logic programming. But those are like encodings for the rules. And the neural part is basically the LLM.
Yeah.
So they have like a reasoning layer that is a discrete layer that analyzes everything and basically comprises with the risk and tries to understand what the user is trying to do, has into perspective not only the data that you're sending, but the overall picture on why this data is being sent. And by doing that, they make a decision saying, this information here can be sent in this scenario, but it cannot be sent in another scenario. So even it's dynamic. Okay.
So what does it really validate? Does it validate data being sent, where it propagates, or downstream agent
remember what I
behavior?
told you. Right now, we don't have this idea of secure pods. Okay. So what we can do to guarantee security, one of the things that is very important is to make sure that whenever we are going to send the data, we do not statically block and allow the data based on just the data being sent, but that you understand the scenario. And based on the scenario, say in this scenario, we can send the data. In another scenario, the data is going to be blocked because in that scenario, it doesn't make any sense to send the data. And they have a reasoning agent that dynamically analyzes the scenarios and creates the rules. And those rules are dynamically created over time.
Dynamic rules created over time based on the scenario, not just the data. And that's the shift. You see, the same piece of data might be completely safe in one business context and dangerous in another. A reasoning layer that understands the scenario, not just what's in the content, but can make that call real time. And here's the thing, defense is only half the equation. The other half is knowing where you are vulnerable before the attacker finds it. And this is where the agentic penetration testing does something the human testers just structurally cannot do.
Suppose that you have the scenario here where you have vulnerability A, where you have an internal database like MongoDB was left accidentally open on the internet. In vulnerability B, you have like a ping, and which has a minor header injection vulnerability. So those two items separately, they may not pose a very high threat, but when you put them together, then they may open like a new type of threat that people have not seen before, and as a result, you need to close it. Okay. The MongoDB could be opening you had a customer issue, so the service business asked them to leave it open so they could basically debug something on the field. but on the other side, another part of IT left that ping open. But then when you put everything together, then it creates a high risk scenario. And because of how things are, it's inconceivable for a human to think of all possible scenarios where those issues could happen. And that creates a huge risk.
You know what is mind boggling? How autonomous agents really think differently.
If you think as a human, you always think about the path you're going to take. And sometimes when you have too many options, you are going to go for the most common issue. I'll give an example. You go to a doctor, you have a cold. Not you have a cold, you have fever and you're coughing. And the doctor will say, I will treat you for a cold. Because a cold is the common disease that will probably involve coughing and involve the fever. However, the coughing. It could be that you have like a COVID and a TB, tuberculosis, at the same time. So because they're happening at the same time, you could have one of the diseases causing the one condition and the other disease causing the other condition, but the doctor would never think about that because the medical doctor always thinking about a single disease first. And by the time you would basically say the treatment is not working, let me try a different thing, it may be too late for you. Okay? That's exactly what happens with the what Ridge does, because it does not think about the common source of the problem that you may have, but it thinks about this is like 1,000 things that could go wrong. These are all the servers and all the connections you can have in your system. Can you basically start staging an attack? And for an AI agent to stage an attack using those conditions.
You see, the doctors always think about one single disease at a time. By the time you realize it's actually two diseases happening at the same time, it may be too late. And that's the composability problem. And that's why AI-driven pen testing catches things human teams miss. Not because the humans aren't skilled, they are, but humans are aware to think one thing at a time, not combinatorially. Now, everything we talked about, the reliability math, the security gaps, the reasoning layer, that's today's problem at today's scale. But what happens when you go from thousands of agents to trillions?
It's very, very easy. It takes a few seconds each attack. So I'm going to talk about my daughter here. When my daughter works today, she has a secretary. And by the way, she is very young, but she has a secretary that prepares her days, tells her what to do and what she needs to do. And by the way, she's going to write for an MBA in the fall. And when she wakes up, she looks at the day, the secretary prepares everything for her. The secretary is an agent. It's not a real person. Imagine a company with 1,000 employees. Imagine that every single employee of that company having like a personal assistant that checks emails, cross-correlate with calendar, cross-correlated with everything on his or her day-to-day business. Imagine everyone in the world having a personal assistant. We're basically saying like we're going to have 9 billion multi-agent systems running in the world just to serve as a personal assistant. Now, transpose that, putting that in every single car, having an agent that takes care of maintenance, communication, self-driving, and everything. And even when you have one car driving in front of another car, if those two cars are as agents, they can be exchanging information. Because one thing that self-driving cars with cameras, they're very bad at, they do not look past this front car on what is the traffic condition. But imagine that those two multi-agent systems, they communicate and they exchange information saying, look, you're driving behind me, but there is another car that is stopping in front of me now. You should start preparing to stop even before I stop my car. So we're heading in that direction. And that's what Project Nanda is basically trying to monitor. Is like, let's create an internet of agents that we catalog and we give certain levels of guarantees for the connection. Personal information is still one of the most valuable assets you have. We are living in very dangerous times. I was subject to an attempt attack, cyber attack, And that attack, I'm basically joking, saying I'm going to create this attack vector right now on my GitHub, because it's very viable to do today. Imagine that I go to your LinkedIn, get your information on LinkedIn, then I go to your Facebook, Instagram, podcast, and I get all information from you. And then I started basically searching the internet using an agentic flow or even Perplexity or Claude. Say, search the internet and tell me which jobs Subrata would like to apply to. And then after I get credible information about those attacks, I contact you as one of the recruiters for one of the companies that have positions open for you. And I mention exactly all the information, credible information. This attack is becoming very, very common in the US. And it's extremely hard to detect that, but it's very, very hard to detect because they basically mixing information from reality with the attack. It's not anymore the person talking about something complete. I'm going to give you $5 million because I was the posted from Nigeria. Remember that email that you used to receive from the Prince of Nigeria? It's called Prince of Nigeria attack. It's not about that anymore. It's about people who basically been able to do the homework on your job, knows what you like, what you don't like, correlate with what's in the world. I was able to catch that because of nuances of the
8 billion personal assistants, every car an agent, every financial transaction managed by coordinated multi-agent systems. That's where this is heading. And if you can't secure agent-to-agent communications today with thousands of connections, think about it. The trillion-agent future, and that's a security problem that we haven't begun to scope. But Claudio brought it back to something immediate, something personal, because the attacks aren't just targeting enterprise anymore. They are targeting you individually using the same world understanding that's supposed to make AI helpful.
cyber attack. And I blocked it in the middle. In the very, very beginning, I said, I just blocked the person and that's it. But it's becoming very scary, those types of attacks.
So here is what I'm taking away from today's conversation. Number one, AI risk is an engineering problem, not an AI problem. We solve reliability for the moon landing. We are just not applying those lessons. Number two, zero trust protects the connections, not the behavior. Once the data crosses your perimeter, you lost control of the other side. Number three, human oversight fails when AI is active. Attention drops to 10 to 20%. The brain enters resting mode. Just validate the results is not a strategy. Number four, reliability compounds. 10 agents at 90% accuracy, system works 35% of the time. And redundancy only helps if errors are uncorrelated, which usually they aren't. Number five, the shift is from static blocking to dynamic reasoning. Rules based on scenario and context, agentic pen testing that finds what humans can't even conceive. Number six, the trillion agent future needs infrastructure that we haven't built yet. Secure pods, reliability guarantees, they don't exist today. And number seven, the attacks are already personal. The world understanding weaponized for social engineering that you can't detect. So if any of these resonated, share it with your security team, your engineering leads, your CTO, and anyone who needs to know it. This isn't just one to listen alone. Subscribe to the Spark on the Porch podcast on the YouTube. Your support means world to me. I am Subrata Kar. Thanks for listening. Bye for now.